Hello, everyone. Dr. Adam Schreckenberger here. I've been collecting some new non-fermenter data from Loyola University Medical Center to gear up for an ASHEX 18XB release. And then it occurred to me that it's been about 4 years since I've done a tutorial, and a lot of things have changed, and the style of the site is now different, so I would like to do a new one. Also, unlike the previous tutorial, which largely focused on just running the web identification programs, our WIPs, I kind of want to jump in and do a little bit more nitty gritty, get into the math a little bit, and really emphasize why I've made some of the improvements and why the 17 version of the matrix and the 18 version of the matrix are both important. So the first thing of note, up on the pshrek.com webpage shown in the left pane, there are three WIPs of importance here: the Vibrio WIP, the Entrix WIP, and the ASHEX 17XB gram-negative non-fermented WIP. You may also notice that there's an ASHEX 14X WIP shown here. This is the legacy version. This was the one that I froze at the time of my father's passing. I figured that there were probably some people out there who would like that version maintained, just dealing with my father's integrity in the field and all that. So it is going to stay there. It is not going anywhere. If you happen to feel uncomfortable with the new changes being made by me, that's totally fine. There's 14X. However, I really do want to get in and say, hey, the 17 version and the upcoming 18 version have a really cool new feature, which I think personally is awesome from a physicist perspective. Remember, I'm a nerdy physicist, and that's how it rolls. There's also the ability, if you are unsure, given your specimen, which whip you should use. The Magi system right here pulls three whips simultaneously and gives you some direction. And there's also some additional information shown on the Aid Cloud tab and some more specific information related to the ASHEX whip shown under the non-fermenter ID link here. You can also figure out where to contact me in the appropriately named About and Contacts tab. So the first thing I want to do before I jump into this is say that the ASHEX 17XB matrix is able to identify over 100 different species of bacteria, represented by 971 clinical isolates, which you can actually see in the key info tab of the matrix itself. This is part of the reason why the Loyola University Medical Center is kindly supplying me with new data. I really want to get to 1,000 clinical isolates. My dad and I used to consider that benchmark like a pipe dream, right? It was the holy grail, I guess, for us to get to 1,000 stored clinical cases of non-fermenters. So we're almost there. Actually, right now, the total is about at 995. So really close, and I'm really excited. So I've pulled a Maldi confirmed Weeksella virosa here. This was identified back in 2014. So I'm just going to run through and actually just plug in the results. Now you may notice that the 17 version of the whip actually fills in everything as negative from the get-go. The buttons are also a little bit easier to use. For example, you now don't have to click specifically on the radio button itself. You can actually just kind of get close enough in that row and it will actually fill in for you, which is pretty nice. When I had that glorious moment there, I was just like, yes, so much yes. So I'm just going to go through now and actually fill all these in, and we'll see how it does. Hopefully it should identify. It's pretty easy to go through and say, haha, I'm going to find the positive ones now because everything else is negative. A little bit easier. This was actually requested by the techs at Loyola who were tired of clicking every button over and over again, which is a respectable and appropriate response. So let's go through, just double check. Now, you may already notice that there is now this new thing at the bottom, this Wilson binomial matrix check. I'm going to get into that later. This is one of those super cool additions that I think is really awesome and should probably be used in some cases. So let's take a gander. Did I get all of that right? Hopefully I did. Once you have all your tests inserted, you just click submit, and it identifies. And I believe this is definitely a match. It positively confirmed Weeksella verosa. And not only did it do it with a very high probability of 99.97%, or 997%, excuse me, it also had a good modal score. So this is a good opportunity to explain what exactly these numbers mean and why do I have two of them instead of just one probability. So this probability number here represents how likely this top candidate is compared to all of the other candidates in the matrix. So all of your different species. Now, of course, this could be a problem. For example, if you have a specimen that isn't in the matrix, right? If it's not covered by this gigantic table, then chances are it's going to still return a high probability because it's going to choose one, but then you need to assess how well it follows the trend, and that's what the modal score is. So whereas the probability gives you how good does this top candidate look against everything else, the modal score tells you, okay, given that you've selected this candidate, how well do your results follow the trends in the data, right? So what you really want to see is a higher probability and a higher modal score. So for example, if this thing perfectly followed all of the trends in the table, this number would be 100, but it's not. So that means that there are some tests that disagreed with the standard. But that's okay, right? That's what makes the beauty of this method more prominent. If you were doing a flowchart, for example, you would have taken a wrong turn and gone down a path that would have probably just wasted time. So that's the benefit of using a matrix method, is that you can assess these pretty much in real time, which is great. And that's what I love. So now that we got that out of the way, I kind of want to explain what the Wilson binomial matrix is about. So the beauty of this method, I'm going to just briefly take away this little icon here and start writing things up. So the beauty of this method is that when you're calculating the probability, it's really assessing a likelihood. And this likelihood is just a bunch of numbers in a product. So it's just multiplying number after number after number. And so let's say you have a 90% in your table, right, for a specific test, so 0.9. If you come in and you assign a positive value here, it's going to come to your likelihood for that specific bacteria and drop a 0.9 in this likelihood calculation. However, if you were to give it, say, a negative value, the number that it would put in here is actually 1 minus 0.9, and so you'd be left with 0.1. So of course, because this is different, this is discrepant with the expected result, your likelihood value drops. So the end result of this is that you get a whole bunch of numbers, and for each bacteria, for each species in that table, you get some probability. And now you're just comparing how likely that is against the total of all of them. And this is actually just the number that gets ported up into this probability expression. Now, this is really great. This is a fantastic method if you have a small number of data points. So for example, there are some organisms that in 30 years of research, my dad only saw clinically once, right? And if it's in the database, if that's represented in the table, which in many cases it is, you can just look in the key info tab of the actual table itself and see, Achromobacter spanius, there's one entry, right? So if you filled in the table based upon that entry, you would find the correct result. However, there's one problem here, and that's why I have included the Wilson binomial matrix. This is actually how sites like eBay or Newegg or Amazon rank things, right? So you have this thing. What happens if you go to a site and you give it 1 like, right? So a thing has 1 like, and that's it. But it has a 5-star rating, right? Let's say you give it the max. Smiley face, right? Well, how does that compare, say, to a product that has 10 likes at 5 stars, right? You would expect that 1 out of 1 kind of means less than 10 out of 10. Now, in the standard probability calculation, that's not true. The standard probability is calculated with everything being on an equal footing. So I've included the binomial matrix because it gives a spread. So everything kind of starts out at, say, 50%. And let's say you have a test that is always positive, right? Always positive. So I'm going to find a good example of this, and hopefully, all right, here's a perfect. Let's look at Achromobacter xylosoxidans, which has essentially been oxidase positive 100% of the time, right? There we go. 63 out of 63. At 63 out of 63, this value is recorded in the standard matrix as 99. We truncate because that, right, if you have 1 minus 1, you get a 0 and the likelihood calculation breaks. So 100% is represented as 99 and 0% is represented as 1. That's perfectly fine. Don't worry about it. It's okay. Well, for 63 entries, the value of the Wilson binomial is 97.13. Let's take a look at something that has less information. So that Achromobacter spanius, for example, also has been oxidase positive 100% of the time. So once again, that organism would be represented in the standard matrix by 99. However, there's only been one occurrence of that bacteria species during the entire time of our data collection. So instead of 97.13 here in the Wilson binomial, or 99, in the Wilson binomial matrix, this is 60.33. So this is a great tool if you happen to have a result that looks a little bit off. And this happened quite a bit, right? And this is where I've repeatedly stressed that these are tools. The ASHEX matrix really shouldn't be used as a definitive ID, right? You should use that as a means to support a definitive identification. And so, for example, when I went back and got the stack of sheets that my dad had left, like that he actually looked at and were just waiting for me after he passed away, I found one of these cases. I found a case where the raw probability calculation actually didn't get it right. And I was curious as to why. And I found that, oh, well, in this case, it was pulling the ID to something that only had 4 data points. And it was ignoring the case that had, 60 data points. And so I thought, well, if I allow the means to weight based on the number of entries in the table, that's going to help people. And so if you check the Wilson binomial matrix, it will perform the calculation with a different matrix. And again, here you see it returns the same thing. In fact, it does a better job at matching to the trends, because now it's factoring in the fact that we have a lot of Weeksella verosa data points in this table. In fact, I think it's over 20. It may even be more than that. 22 entries in this table. So the Wilson binomial is a really nice tool. I love having it in there, and it's just another option that you can use to help make an identification. But I can't stress enough, I've always been big on pushing the concept that these are tools. In fact, the name, like ASHEX, is actually an acronym. It's like Adam's Simple Helper Experiment, because when I started, this was just, oh, hey, I'm going to try something cool for my dad and see what happens, right? So it's meant to be a helper, not a definitive ID. So I just want to point that out. I hope people really like this tool. The mathematician, physics guy in me kind of nerds out about this. So I hope that it helps you all. And I think that kind of concludes the basic gist of the tutorial portion. So I guess I will say that there are big things on the horizon. As I mentioned, we're getting pretty close to having 1,000 specimens in this table. Or I guess I shouldn't say specimens, but 1,000 isolates. So I'm really excited about that, and I have to give massive thanks to the people at Loyola University Medical Center who have been totally supportive of getting us to this goal. I guess I should also once again state that ASHEX is entirely open source. All of the data is stored. So if you download the raw table, like this Excel file, you don't just get the matrix, you don't just get the key info or the Wilson binomial matrix. You also get all of those tabs, which I kind of poked into earlier, which gives you the raw data itself. How many actual positive and negative test results were recorded for these organisms. I was really big on that when I started this in high school, and it kind of stuck with me. So there it is. It's been maintained. I hope people find it useful still. And I have to say, this isn't my field, right? I've already said that I'm a physicist a few times in this tutorial. But I have to tell you guys and girls and ladies and gentlemen that out of all the things I've done, I'm really proud of this thing, possibly more than any other scientific tool. It has assisted in the identification of over 18,000 organisms since the WIP was published. And that is incredible to me. And it's been used by people all over the world. And so I'm really glad and humbled that it's assisted and that it's helped and that it's made a difference. So it's going to stay. The site's not going anywhere. I made that pretty clear in my December 9th post on the website, and I stand by it. The site isn't going anywhere. As long as I'm around, this tool will remain to help and identify. So with that being said, I hope you have found the tutorial useful. I hope you all continue to use it. I hope you forgive my totally math nerding out and scribbling numbers on my paint tool side canvas. And with that being said, have a good day.